Okay. Okay, so for this one, go ahead and take a picture of the screen because I'm going to go to a whiteboard in a second. Yeah, so, okay, so NO2 is brown gas. We gave you the rate constant and the reaction. So write the rate law for this reaction. Does anyone want to raise their hand and tell me what they got? Yeah, Fatima.
Isn't it just rate equals K of NO2 squared?
Say that again.
Rate equals K NO2 squared.
What of NO2? What property?
Oh, the concentration of NO2. Or not the concentration, the pressure.
Yeah, there you go, the pressure. So in this question, we're talking about gases, and we don't measure gases with concentration, we measure it with pressure. That's why your K value is in inverse atmospheres times inverse seconds. Okay, so Fatima was right. It is rate equals K times pressure of NO2 squared. And your K value is 25.4 atmospheres per second, inverse atmospheres times inverse seconds. So for solving that one, you have to know the order of the reaction. There are two ways that you could have figured that out. The first is that we gave you the units for the rate constant. It's inverse atmospheres over inverse seconds, so that must be second order. The second way you could have known, it depends on if you've watched the lecture from Monday. If you haven't, you should do that before class. But yeah, we told you it's an elementary reaction. So you could have used the stoichiometric coefficient of 2 to say that it was just NO2 squared, pressure of NO2 squared. But if that way doesn't work for you, don't worry because we gave you the rate constant and it'll make more sense tomorrow. Okay, so part B, if the initial pressure is 0.263 atmospheres, what's the rate at T equals 0? Someone raise their hand and tell me what they got there. Yeah, John.
Could we use integrated rate law for this one?
For this one, you could. There's an easier way to do it, but you could. What'd you get?
I mean, I just said the pressure, initial pressure is equal to the final one because it's at T equals 0. But I'm not super
Actually,
sure.
you could not use the integrated rate law because we're looking for a rate in this case. But let me go to one of your classmates and see if they can help you out with this one.
Yeah, I'm not sure about this as well.
Yeah, no worries. No worries. But that's why we're here. Okay. Isabella, what'd you get?
I'm a bit unsure on units, but I got 1.77568.
Yeah, that's it for the value. Albert, do you know the units?
Is it in atmospheres per second?
Exactly, it's atmospheres per second. So the final answer will be 1.76 atmospheres per second. And the way that you would work that out is since we have the rate law from the first reaction, from part A, we know that rate equals 25.4 inverse atmospheres times inverse seconds times pressure squared. And in this, we gave you the initial pressure. So you just plug that into your rate law from part A. And then your units, of course, are going to be atmospheres per second because those are always the units for rate when you're talking about pressure.
I have a question. Should it be a negative rate?
It will not be a negative rate, no.
Because aren't the isn't NO2 decreasing? So wouldn't that make it negative since it's going down?
Yes, but we always call rates positive.
Okay.
Sorry, can you
Me-
explain how you got the rate one more time?
The rate law,
No, the rate for part B.
the rate for part B. Yeah, so we have the rate law from part A, which is rate equals K times pressure of NO2 squared. And we have the K value because it was given to us in the problem. And then in part B, it gave us the initial pressure, which is 0.263 atmospheres. So you would just say rate equals 25.4 times 0.263 squared, and that gives you 1.76. Okay. Sarah, could you stop sharing your screen, please? Thank you. Sarah, can I only see the whiteboard?
Versus what else?
Okay, no, that's good.
Always the whiteboard.
Okay. Oh, John, did you have a question?
Yeah, I was just saying, like, we use the answer from A to solve B, right?
Yes.
But it says at time equals 0, so it's a tricky case, I think. It's not like time equals 5 or something, but how did we incorporate time into the rate law, which doesn't have time in it?
So with initial rates, whenever we ask you for an initial rate, that automatically means time equals 0. But in this case, we gave you the initial pressure. So you don't need to worry about integrated rate laws or anything else because you know what the pressure is at time equals 0. It's 0.263 atmospheres.
Yeah, so that's because the rate law provides us with the rate at time equals 0 by definition, right?
Yes, it can.
Okay. Yeah, thank you.
Okay, so for part C, we are asking you guys to do some graphing. So the first thing I'm going to say is I really hope you labeled your axes because you always should with your graphs, and we even told you in the directions. Okay, so we'll start with this first one. This is absorbance versus time. So does anyone want to tell me what their graph looked like? Just kind of describe it for me. Did you start out high and go low? Did you start at 0 and curve up? Fatima.
I did mine to where it was like the inversely proportional graph, so it like starts high and then does the weird curve thing down.
So kind of like this.
Yeah.
Yeah, that's exactly right. So first of all, we need to remember that pressure is proportional to, I need to move your faces. Pressure is proportional to concentration, which is N over V. We know that from the ideal gas law. And that is proportional to your absorbance, A. Okay, so high pressure means high absorbance. Okay, and so if you look at the reaction we're given, you've got 2 moles of NO2 forming 1 mole of N2O4, or in terms of pressure, it's 2 atmospheres of NO2 forming 1 atmosphere of N2O4. So this means that the pressure is going to be highest at the beginning of the reaction and lowest when the reaction is complete. So then at high, when the temperature or when the time is low, we're going to have a high absorbance because we still have a high pressure. And then as the reaction goes on, we're going to have a lower pressure, so we'll have a lower absorbance. Yeah, Nikita.
Could you go over what absorbance is?
Okay, so for absorbance, if you have a spectrophotometer, it's basically you shine light through a sample and then you measure how much light is absorbed.
Okay, thank you.
Yeah, so when the concentration is really high, that means a lot of stuff's going to be absorbed because there's so many particles in the way, if that's an easy way to think about it. Okay, so that is the graph for absorbance versus time. So now let's look at rate versus time. So rate, time. Does someone want to raise their hand and tell me what they got for that? Yeah, Albert.
I got like a parabolic curve that was going upward, so the rate increases over time.
So you got kind of like this.
Yeah.
Okay, okay. Did anyone get anything different? McKenna.
I got essentially the opposite, like the same thing as absorbance versus time.
Okay, so you got like absorbance versus time. Okay, so we have two kind of different ideas on this. So let's look at it. Let's see what we can come up with. So rate versus time. There's two ways you can think about this. But I think the easiest way is just to look at our rate law. So we have rate equals K times pressure of NO2 squared. Okay, so this is just a second order rate law. Okay, and so we know what those look like based on the graphs that we did during our PhD days. And so the correct answer is actually going to be what McKenna told us, which is starting high and decreasing over time. Okay, and another way to look at it is if you remember our reaction, it's 2 atmospheres going to 1. Okay, so we're using up all of our reactant as we go. And because we're using up our reactant, it's going to be harder and harder for this reaction to move as quickly because we have less of our starting material. Okay, so our absorbance and our rate graphs both end up looking the same or similar. It just starts high and then it curves down over time. Okay, so now we have a few questions. Okay, Nikita.
My bad, I forgot to put my hand down.
Oh, okay, no worries. John, did you have a question?
Oh, same here. Sorry.
William.
Yeah, I might have missed you referring to this, but I mean, never mind. It looks like it's referred to. I was just going to say that the rate versus time would be like twice as dramatic, probably, or much more dramatic than the.
Yeah, you're right. It would
absorbance.
actually, it would curve
Right.
a little more sharply than absorbance
Yeah.
would. Yeah, I can. Here, I'll even
No, it's fine. I'm
exaggerate that a little more.
That was.
Yeah, that's a minor thing, so I wasn't gonna get into that. But yeah, the rate would technically be curved down a little bit more than absorbance, but that's minor. Anyways, now it's the last one, which is rate versus absorbance. This one's a little trickier, but does someone want to raise their hand and tell me what they got? Jacob.
So I got the same shape as the first two, but like it starts low and goes up as we increase.
Could you say that again? Your voice was kind of low.
So like it's a similar shape to the first two graphs, except it starts low and like goes up as absorbance increases.
Okay, so kind of like this. Is this what you're saying?
Yeah.
Yeah, perfect. Yeah, that's exactly right. So the way that I would do this is you can kind of look at what you've done with these first two graphs, because in both of these graphs, you're comparing absorbance and rate to time. Okay, so we can use that fact to figure it out. When time was low, so down here, absorbance was really high and rate was really high. Okay, and then over time, as time increased, absorbance got low and rate got low. So rate and absorbance are reacting the same way over time. Like they're both high at the beginning, they're both low near the end. So they must be proportional, not necessarily directly proportional, which is why we don't have a linear graph, but they're in some way related so that as one increases, the other increases. Okay, so then your final graph ends up being like what I have drawn right here. Victoria, do you have a question?
Yeah, I was wondering if you could, like, for the rate versus absorbance graph, you could just look at the rate law, because like pressure and absorbance are proportional. So you could like look at the rate law in terms of absorbance and then like see that it's like it takes the form of like a parabola. Like
Yeah, that's a great way to look at it. So just to repeat that for you guys, she looked at our rate law, which was rate equals K times pressure squared. And because pressure is proportional to absorbance, she just said that it must be parabolic, so curving upward. Yeah, it's a great way to look at it, Victoria. Those who have their hand raised, is that a question or still left over?
Yeah, I have a question.
Okay.
So you answered some of the questions partially, I think, but I was just wondering, how do we specifically compare the rate law or rate and absorbance? And also, so pressure is directly proportional to absorbance and rate is proportional to pressure by the second power, right? So I would just say if pressure is directly proportional to absorbance to the power of 1 and rate is proportional to pressure by a power of 2, wouldn't we get like a straight line? Not a straight line, but a y equals mx plus b type of line?
No, and the easiest way for me to explain that is just if you look at the rate law, because we have rate equals pressure squared, K times pressure squared. So that's like saying rate equals constant X squared, which would have to be parabolic.
Yeah, but in the third graph, aren't we comparing kx squared with kx? Like if you were comparing kx squared with 1, it would be a parabolic line or with a constant, but we're comparing it with kx type of thing because we say that pressure is proportional to a to the power of 1. So I was just thinking, like, if we divide both of them, we would just get something like rate over absorbance equals kx.
I think you might just be overthinking this one. That is, yeah, because you really don't have to do all of that manipulation to figure this graph out. But I would say definitely chat Cynthia or Sarah if you're still confused on this, and they can probably explain it a little better than I can.
If you're confused, just briefly, you can literally use the rate law and plot like 4 or 5 different points on this, and you'll see the exact trend that we've drawn here. it's not a very hard
Yeah.
calculation.
Yeah.
Okay, so go ahead and take a picture of this or write this down, this whiteboard stuff, if you haven't already, in the next 3 seconds or so, because I'm going to clear this. 3, 2, 1. Okay, so part D, does someone want to raise their hand and tell me what they got? Victoria.
I got 0.0829 atmospheres.
0.0829. You're very close, but that is not quite right. But that is on the right track.
Okay.
McKenna, what did you get?
I might have overcomplicated things, but I got 0.173 atmospheres.
Yeah, that's exactly right. You didn't overcomplicate it at all. Okay, so let's go over this one. So we gave you the initial pressure, which is 0.263 atmospheres, and we're asking you for the total pressure in the flask after 0.325 seconds. Okay, so we're talking about what's happening in the reaction at a certain time. So the best thing to use here is going to be our integrated rate law. Okay, so that's going to be 1 over P equals 1 over P. Notice I'm using the second order version because it's a second order reaction. So this will be pressure initial plus KT. Okay, and the thing we want to find right now is this. We want to find our pressure at this point. Okay, so what we can do is just say this equals 1 over 0.263. Excuse the handwriting, but you get the point. Plus 25.4 times our time, which is 0.325. And with that, if you solve all that, you'll get that the pressure after 0.325 seconds equals 0.0829 atmospheres. Okay, so that's the pressure of NO2 that's remaining in the flask after 0.325 seconds. Okay, now some of you might have stopped at this point, and that's why I said with one of your colleagues who gave this answer that they were on the right track. Okay, so you always have to remember what the question's asking you. Okay, we want the total pressure in the flask. This is just the pressure of NO2. This is a partial pressure, but we have to account for the pressure of N2O4 that's also been made. Okay, so we've got some pressure of N2O4 and we need to find that before we can get our total pressure. Okay, so with that, we can think about how much NO2 we've used. Okay, so we started out with 0.263 atmospheres of NO2. And we now have this much, 0.0829. So if we subtract this, then we get 0.1801 atmospheres. Okay, and that's the NO2 that we used. Okay, we used that many atmospheres in the reaction. So if we look back at our reaction, for every 2 atmospheres of NO2 that we used, we made 1 atmosphere of N2O4. Okay, so that's just working with your stoichiometry again. So if you take this value and you divide it by 2, then that gives you 0.09005, and that's atmospheres of N2O4. Okay, so that is our pressure of N2O4 after 0.325 seconds. So now we can look back at the question. We're asking for the total pressure. So all we have to do now, Dalton's law of partial pressures, just add this value and this value. So our total pressure will be 0.0829 plus 0.09005 equals 1.73 atmospheres. And this is our final answer. Okay, so does that make sense to everyone? Does anyone have any questions? Nope. Okay, so I'm going to give you about 5 seconds to take a picture of this, and then I'll stop sharing, Sarah, so you can put the slides back on. Okay. Oh yeah, on that last problem, that was supposed to be 0.173, not 1.73. That was just a typo on my part.
If y'all can answer the poll about more time.
Okay, most of you guys are about done with this one, and we have a few more questions to go. So I'm gonna go ahead and go over it. So question 4, we're talking about carbon dioxide and neon in equal moles at equal temperature in identical containers. And we're just looking at these two statements. So statement 1 was saying that the two gases have equal pressures. Does someone want to raise their hand and explain to me why that would be true? Yeah, Sid.
So you have same number of moles of gas, and just looking at the derivation, we can see that pressure is proportional to like the frequency of collisions and the force of each collision. So if we have like the same number of moles, we should ideally have the same frequency of collisions. And if we're at equal temperature, then the relative kinetic energy and average speeds of the molecules should be the same. So even if the masses are different between the molecules, mv squared should stay the same. So pressure should be the same between the two gases.
Yeah, perfect. So just say that again. We know that the kinetic energy is going to depend on our temperature, not the type of the molecules. So since our two flasks are at the same temperature, they're going to have the same average kinetic energy. Okay, so they're also going to have similar speeds. Okay, but since neon is lighter than carbon dioxide, the neon molecules are actually going to be moving a little bit faster. If you think about that equation for root mean square speed, we know that the mass matters. Okay, so even though their kinetic energies are the same, their average speeds are going to be different. But these two gases do have equal pressures, so they must be exerting the same force on their containers. So like Sid said, we measure pressure with the frequency of collisions and the force of collisions. Okay, the neon molecules are lighter and they're moving faster. Okay, so they're gonna hit more frequently, but they're not gonna have as much force with each collision. The carbon dioxide molecules are heavier and slower, so they're gonna hit less frequently with a lot more force. It's like if I throw a tennis ball versus a bowling ball. The tennis ball is going to hit more frequently, but the bowling ball is going to hurt more. Okay, so therefore, on average, the frequency and forces of collisions cancel out to where their pressures are going to be the same. Okay, so that's for the first part, but for the second question, they have different rates of effusion. Does someone want to raise their hand and explain that one? Yeah, Prisha.
I just used the VRMS equation and said, so the hour speed equals the square root of 3 RT over M. And since Ne is like lighter than CO2, I said it would have a faster average speed and therefore it would diffuse faster or effuse faster.
Yeah, yeah, I like that answer. Good job. So another way you could do it is to look at Graham's law of effusion. So the rate of effusion is inversely proportional to the square root of the mass of the molecule. Another way of saying that is just heavy molecules effuse slower than lighter molecules. And that also makes sense if you look at it from the root mean square speed equation. If you've got a heavier molecule, it's going to be moving slower. So it's going to effuse more slowly. So neon is lighter than carbon dioxide, so it's going to effuse faster. Okay, so that's it for question 4, unless anyone has any questions.
Yeah, one question I have is which postulates and conclusions of the kinetic molecular theory did we use? Because in the textbook I saw 4 postulates, and it didn't really seem like we used very many of them in this question. It seems like we just kind of answered it logically using a few different equations we've found out.
Specifically, you would use kinetic energy is proportional to temperature. And
Okay,
then, yeah,
is that a postulate?
believe so.
Okay. Maybe I'm just confused then. I'll try to go back and fix that.
And Jacob.
Yeah, I kind of had the same question. I was just wondering when it says using the postulates and conclusions of the kinetic molecular theory, do we actually have to like explicitly state like which postulate we're using and then back it up?
Yes, you should state which one you're using. But backing it up, like if you mean like deriving it, no, like just saying like according to the kinetic molecular theory, kinetic energy is proportional to temperature, and then go on with your explanation, that would be fine. But yes, because it does ask you explicitly to use the KMT, you do have to use that. Okay,
Okay,
so
thank you.
yeah, at this point, oh, John, do you have a question?
Yeah, for the first question, I said this happens because in low pressures, gases just obey the ideal gas law, and one of the postulates of the kinetic molecular theory or the ideal gas law is that we ignore the intermolecular forces, so we don't see any differences in pressure for different elements. Would that be a valid argument for this question?
It wouldn't be enough. It would be on the right track, but it wouldn't be enough to get full credit. Okay, so Sarah, I think you can go to the next one. And if you guys have any more questions, just chat one of us.
I'll give you like 2 more minutes. Okay, we're gonna go ahead and go over this one. So for part A, it asks to briefly explain any changes to pressure caused by the temperature change using understanding of KMT. So who wants to answer that one? Victoria, go ahead.
So I said that according to the kinetic molecular theory, temperature is proportional to average kinetic energy. So if you decrease the temperature, then you're decreasing the kinetic energy. And we know that kinetic energy is equal to 1/2 mv squared. So when you decrease the kinetic energy, you're slowing the speed of the molecules, and that means they're hitting the walls with less force and frequency, which means less pressure.
Yeah, that was perfect. So the only thing I would add is the link between hitting with less frequency to less pressure is that pressure is defined as the result of the force of the gas molecule collisions with the wall. So because we have less forceful gas collisions and less of them, just like Victoria said, we have a decreased pressure. That's perfect. What about part B? Does anyone want to kind of explain what they have before I whiteboard draw it? Chelsea, go ahead.
I feel like linear just like increasing, so pressure increases, pressure increases, and then for the second one, it's just like the slope is decreased, but it kind of rotates so that it still will go through the origin.
Yeah. So I will really quickly whiteboard this. And this is T. Oh gosh, Lottie's much better at the whiteboard than me. That's supposed to be a K. And then this is a P. An A. T. That is awful, but hopefully you guys get the vibe. So the important thing to note here is they're both going to be intersecting at the origin. So we'll have our first one, something like this, at 5 liters, and then our next one, something like that. It's not quite different enough. Something like that at 10 liters. So it'll look something like this. And again, important things to note, intersect at the origin here, and they do not have the same slope. So if you were asked that, the answer would be no. They do not have the same slope.
Do we have to make like the lines dashed like up to a certain point?
So if you were to do that, it would be around like this box here. They would be dashed through. You don't have to, but it does show that you know that it's very unlikely that it goes to 0K. I don't think they'll take off if you don't dash the lines, but they also won't take off if you do.
Okay.
All right, and then on part 3, that is not the right thing to share. I want this. Where is it? Sorry, I'm having technical difficulties. Okay. There we go. On part 3, I have a poll that I am going to go ahead and launch. So I will give you guys 30 seconds to fill in your answers. Just lost my poll. 5 more seconds. Okay. So for the root mean squared speed, who wants to explain why they got neon as greater? Sid, go ahead.
So the neon molecules are actually smaller in molecular mass. So from like the VRMS equation, I guess you can see that it's inversely proportional to molecular mass, or like the square of it. So therefore, it should be it should have a higher VRMS.
Yep. So the VRMS equation states that the root mean squared speed is equal to the square root of 3 RT over M. So that means M is inversely related to the root mean squared speed. And since neon has a smaller mass, it has a greater root mean squared speed. What about the mean free path? Who wants to explain that one? I'll just explain it. So the mean free path equation is RT over the square root of 2 pi, square root of 2 times pi times diameter of your atom squared times Avogadro's number times pressure. That's all in the denominator with RT in the numerator. So the thing that we're going to factor in here is the diameter of the particle squared. The diameter of neon is smaller than the diameter of argon, so therefore it will have the greater mean free path. And finally, average kinetic energy. Can someone explain why those are equal? Harveen, go ahead.
Average kinetic energy is dependent on temperature change, and they both have the same temperature.
Yep, exactly. Average kinetic energy is 3/2 nRT, which you see that there's no factor in that equation that is different between the two, so they're equal. Great work, guys. Any questions on this? Yeah, Mamadou?
Yeah, could you explain a bit like on the mean free path of argon and
Yeah, so the equation for mean free path this is actually what I had. It's hard to like speak out, so I will just show it to you guys. Is if I still have it open. Is this down here in the bottom. So it's RT over square root of 2 pi d squared NAP. And if you look at diameter squared, this is diameter of the particle. So the diameter of a neon particle is going to be smaller than the diameter of an argon particle. And because of its smaller diameter, you can see that diameter is inversely proportional to mean free path. So therefore, smaller diameter means greater mean free path. Any other questions?
And how did you know the diameter of neon? Like, did you Google it or like how?
No, but if you look at your periodic table, right, you can see, like, you know your trends, right, from Gen Chem 1. And so you would inherently know that neon, which is a noble gas, and argon, which is a noble gas. So you know that the decreasing across doesn't have an impact. The only thing that's going to matter is the increasing down. And neon is this one here. It's 10, and argon is 18. So neon will be smaller than argon. You don't actually know the number, but you know them relative to one another. Okay. Any other questions? Then we'll go ahead. Oh, wait. I don't actually have my participants thing open. Any other questions? No. Okay. We'll go ahead and move on to question 6. And this one's just a multiple choice, so we'll give you guys like 2 minutes.
All right, so we're gonna go ahead and run through this one. So basically what's happening is that there is like shower, there's a one barrier, and on one side we have a lot of hot water vapor like entering the air, right? So the first answer choice asks, there is more water vapor in the air inside the shower, so there are more moles of gas inside the shower relative to outside. So does anyone want to share why this one is incorrect? Yeah, McKenna.
My logic was, according to Avogadro's law, if we have more moles of gas, then we should expect the volume to increase, and the curtain doesn't billow outwards, so that one's wrong.
Perfect. Yeah. All right, so then for our next answer choice, it asks, there is more water vapor in the air inside the shower, and since H2O weighs less than N2, the air inside is less dense, which pulls the curtain in. Does anyone want to share why this one is also incorrect? Okay, well, for this one, it's kind of like arbitrary. So we don't really know how much N2 is inside the shower. So we can't really say this, but even if we were to just go along with it and say that because you have more H2 inside, that means that you're still hitting with greater frequency and greater force. So we can assume there's also N2 on our side. So we're hitting with more frequency, and so it again billow out. Okay, and so for the next answer choice, it's saying that the air inside the shower is hotter. So to keep pressure constant, the volume must decrease. This one is also incorrect. Why is that? Yeah, William.
If we wanted to keep the pressure constant when temperature increases, you would have to increase volume.
Right, and so also this this answer choice is kind of it goes on that verge of us saying oh, the particles know what they're supposed to do. So we can't say the particles just know that they have to decrease their volume because they want to keep pressure constant. So instead you have to actually walk through the process of saying that, because it's hotter, that means the particles are moving faster, that means they're colliding more, and therefore volume would actually increase. And then so for the last one, it's saying that the air inside is less dense due to the increased temperature. So the pressure outside the shower curtain is higher than inside. And so this one is correct because, as we know, we increase the temperature within the shower, which means that these particles are moving faster, and that means that they're spreading out and apart. So that's creating more space, and that means that the air inside is less dense than the air outside, which is cooler and more dense. And so if the outside air is more dense, that means that the particles are hitting that barrier more often. And so because of that, then you're going to have that billowing in. So because, to answer the question in the chat, if you're increasing your temperature, everything's moving apart and away. So you're just creating more space between the particles.
So we're assuming that the air is just so there are just fewer moles that are in the shower. You're saying it's just sort of diffusing? Because if the air gets less dense, you say they're just moving away. We're assuming that they're actually leaving the shower. They're going from inside the shower to outside the shower.
Right.
Is that correct?
So it's just kind of becoming less dense. They're all kind of floating out.
Okay.
Yeah. And then can we explain C again? So basically, if you were to go along with it, the air inside the shower is hotter. So to keep the pressure constant, the volume must decrease. So the particles themselves don't know that they want to keep the pressure constant. So like the air particles are just trying to like, they're just moving. So if you're increasing the heat inside the shower, that means that the particles are going to be moving. They're going to have like pressure going against like that shower curtain. And so like instead the volume would increase.
I have a question. So for D, like if the air inside has an increased pressure, an increased temperature, wouldn't that mean like the particles are moving faster, which would like also increase the pressure on the curtain?
Yeah, I think this is going back to like William's question where we were saying that they're like diffusing kind of like outwards. So yeah, in theory, yes, if they were like actually colliding with the wall with more force, then yes, the pressure would increase. And so then it like would do the opposite of what we're saying. But because we're saying that it's becoming less dense and diffusing, therefore like there's less actually hitting that wall. And so the outer force is going to push it in.
Yeah, and I actually kind of disagree with that. I think that this question probably isn't worded very well. I think you would probably have to say something about how the air can actually leave the shower. Because the examples we've learned about like balloons and stuff, they've been all closed systems. So
yeah, this might have been like a little confusing. We just take them from past exams. So this was on an exam before. Yeah.
If it makes you guys feel better, it was on my exam and like a lot of my class missed this question. So, but it's good to understand why this happens. And the explanation, because the shower is not an enclosed system, it allows for pressure movement and particle movement between. So a balloon's an enclosed system because you tie a knot in it, and therefore a particle inside a balloon has no way of escaping. A shower is not an enclosed system. You have a rod and air escaping above. You have a curtain that allows air to escape around. So therefore it's not an enclosed system, and you can have particles moving within the barrier of inside to outside. And for time's sake, we're going to go ahead and move on to question 7. If you have further questions, you can chat any of the TAs. Okay, we are going to go ahead and go over this one, and for time's sake, I am just going to go over the answer instead of having one of you guys go over it for us. So here we're supposed to explain how intermolecular attraction should affect the pressure of a gas using KMT. This is an idea that should be pretty cemented in your mind by now, so this should be a relatively easy one for you guys to answer. But basically, if the molecules of a gas are attracted to one another, then the attraction will provide a force that will decelerate the gas molecules as they approach the wall of the container. So thus, a particle that's nearing the wall will be slowed down relative to the speed if there were no attractions to one another. So when they hit the wall, they'll do so with less force than expected because they have less speed. And because they're hitting with less force, we know from kinetic molecular theory that the kinetic energy is directly related to the pressure, and that can derive to tell us that the force is related to the pressure. And therefore, this will reduce the pressure relative by that predicted by an ideal gas. However, at a normal condition, the effect of intermolecular attractions is so incredibly small that each interaction between the molecules is relatively microscopic, so summing up all the collisions really won't result in enough change to actually be measurable relative to an ideal gas. That's why you need such a high number of collisions or a high particle density for the effect to actually be measurable. And again, we said it a little bit earlier, but like by high density, we mean like 100, 200 atmospheric pressures, not like 5 or 10. So it's like very high. And then like very, very high density is like 400 to 500 ATM. So it's not anything you would be capable of making like on your own as a human, unless you're really strong. Any final questions on this? Yeah, John, go ahead.
Can you explain again why or how you observe a positive deviation? I understand the negative. It's because of the polar molecules just attracting each other more and dragging each other down. But
right.
when we have very high like
a positive deviation means that we're at very, very high gas densities, right?
Mm-hmm.
So when we're at such high gas densities, like again, hundreds and hundreds of ATM, the particles have nowhere to go except to be placed essentially like right next to each other. And when they're right next to each other, a particle is not going to want to attract to that if it's forced to be placed like essentially in the same exact spot as another particle, and will instead repel from one another. So when you repel something, you push on it with a greater force than if there were no repulsion whatsoever. So therefore, it'll have a greater speed, it'll hit with greater force, and it'll increase the pressure.
It's like literally the particles have nowhere to go. So they just have very high.
Right, the particles are so close together that they're pushing away from each other and want to hit the wall instead of hit another particle.
Yeah, okay. Thank you.
Okay. And Jim?
Yeah, can you explain again the second part of this question? Like, can we do this without talking about positive and negative deviations?
Do which part? How
like how room temperature leads to
yeah. So
yeah.
No, you can't do it without talking about positive negative deviation, because we just talked about positive negative deviation to answer the first part, and we use the fact that those positive negative deviations don't happen to reason that there's negligible interactions. So you don't like specifically write the positive negative deviation part necessarily to answer the second sentence, but you relate it back to the positive negative deviations we saw earlier in the statement, and that's why you're allowed to say negligible interactions.
Yeah, isn't the argument basically just that it remains linear regardless of your density? So that like an increase in density would have the same impact as a proportional decrease in volume or increase in temperature, so you don't see any of that deviation that you would see with attraction.
No, so it's not like, it doesn't have to do with like proportions or density or anything, right? Because if it were related to density, you wouldn't see that impact at all, right? Because then the attractions would still matter. But you have to factor in that the attractions, because intermolecular attractions like don't go away. They still exist, but when you have particles that are so far apart from one another, the attraction of a particle to another one is going to be such a microscopic number that when you add up all those attractions and the relative increase or decrease in force from an attraction or a repulsion, it's going to be so microscopic and minute that it won't have any impact relative to what we saw in ideal gas law. And that's like the only way you can explain it.
Sure, thank you.
Yeah. Okay. Any other last questions on this one?
Can you go back to question 6? I just wanted to get a picture of it.
Yes. Did you get it?
Yeah.
Okay. Cool. I'm going to go ahead and stop share. That is the end. Thank you all for coming. And if you have any questions about problems we went over, you can email any three of us, or if you know the problem, you can probably also email whoever your respective TA is too.
Thank you.
Thank you, guys.
Thank you.
Thank you.